Yeah, good morning to all of you. In this session, I would like to discuss certain theoretical aspects concerning steady-state process simulation. In fact, I'll be dealing with this particular topic in two parts. The first part, I'll be dealing with certain theoretical aspects of modeling, simulation, various aspects, followed by certain aspects that you need to know in order to conduct process simulation using any process simulator that will be taken up in the next session. Now, this is what I expect from you at the end of this theoretical session. You should be in a position to identify clear-cut difference between these three terms: modeling, simulation, and optimization. And then you should be in a position to identify what are all the benefits that you will be able to derive using process simulation. And maybe I'll spend some time in showing you the role of property estimation in conducting process simulation. What is the role and what is its importance in conducting process simulation? So let us go ahead. So process simulators, for example, like Aspen, ChemCAD, Pro2 and so on, they have become really an indispensable engineering tool to chemical engineers. It may not be an exaggeration if I try to say there is no such versatile software available in any other branch of engineering which is as capable as something like Aspen or some of the process simulators that we have in our branch. So literally, whatever tasks a chemical engineer is expected to do, you will be able to take the help of a process simulator in discharging some of those tasks most effectively. In fact, these process simulators are continuously being developed by incorporating newer models for different equipment, design models, cost routines, and also optimization tools. In this respect, if you try to compare the capabilities of Aspen maybe about 10 years back to that of now, there is a seesaw change. This is one issue. In the beginning, sometime back, people were thinking that process simulators can be effectively used while teaching design courses. But now, with my experience, I can definitely suggest the use of process simulators can be integrated throughout the curriculum while teaching several courses. Like we'll be able to make use of a process simulator to effectively teach some of these courses like mass and energy balances, fluid mechanics, mechanical unit operations, heat transfer, thermodynamics, mass transfer, reaction engineering, process dynamics and control, safety and design. Practically, you can see from this list that we will be able to do in most of the chemical engineering core courses. We'll be able to take the help of a process simulator and solve most of the problems that we'll be teaching in undergraduate study or maybe postgraduate study. In fact, another advantage is we will be able to use this as an important pedagogical aid while explaining some of the concepts dealing with some of these core courses. And as you can see, process simulators are widely used in several industries: chemical, petrochemical, refineries, pharmaceutical, fine chemical, and even in biochemical industries. As time progresses, more and more capabilities are being incorporated. As a result, you should be able to apply process simulators for whatever application that you intend to do. Now, one of the major advantages of a process simulator is every process simulator has a very large property data bank for estimating the necessary physical properties. Not only this, normally the physical property data bank will be having properties with respect to pure components, but as you are already aware, whenever we deal with any process stream, it will be always a mixture of components. So we need to use certain property methods to calculate the required properties of a mixture. So the advantage with a process simulator is the process simulator not only has the pure component property data bank, but also various methods are incorporated in order to calculate the required properties of a mixture. For example, the vapor liquid equilibrium, the bubble point temperature, dew point temperature, and so on. But I may be failing in my duty if I don't try to say, bring out this drawback. You may be in a position to construct your simulation model, solve a problem, but you may not be able to know what are the actual calculations that are done by the process simulator in the background. You will be able to define the problem and maybe look at the results. What actually happens inside may not be visible. In other words, it can be considered as some kind of a black box. Probably, especially when teachers are trying to use some of these models, enough care may have to be taken in explaining some of the background calculations or maybe some of the limitations under which such calculations are made. So coming to, I may not be going into many details, probably by now every one of you is aware of what is meant by modeling. For example, a model is an imitation of reality. And just go through these statements. For example, if I want to talk about the effort of modeling, one should think of these three important characteristics before thinking of developing a model. What is the actual system? The first one is, what is the actual system for which you are trying to develop a model? Is it a reactor? Is it a distillation column? Or is it some other thing? Then the second important thing is, what is the purpose for which you are trying to develop the model? Then the third one is, how accurate the model developed is. So let me cite a small example. Consider, for example, an operating reactor in a process plant. Now, for some reason, I would like to find out the optimum temperature at which the reactor must be operated in order to get the maximum possible conversion. Now, do you think what are the possible options that you have? The best bet obviously would be, you should be in a if it is possible, you should be in a position to experiment with the actual system, vary the temperature at which the reactor is operating, and maybe measure the conversion that is obtained. As you know, in an operating plant, that kind of experimentation may not be permitted because it leads to loss of productivity, variation in product quality, and it may be very costly. So just because you are not permitted to experiment, do you think we should give up this particular topic? Optimizing temperature, if you are able to improve the conversion, probably you may be able to improve your profit. So just because you are not in a position to experiment, you need not have to give up this particular problem. Now coming to this particular aspect, let me identify the three important things that I was talking about whenever you think of modeling. What is the system that I have in mind? Let us consider the particular type of reactor which is in operation in an existing plant. It can be a CHTR, PFR, or maybe any other type of reactor. So that is the actual system. What is the purpose? The purpose is to identify a relationship between the temperature and the exit conversion. Once I have such a relationship represented in a mathematical form, I may be in a position to find out what is the optimum temperature at which the conversion can be maximized. That is the second part. What about the third part? How do I know how accurate the developed model is? Then for this, you may need to have either some amount of plant data or maybe some type of an experimental data in order to validate your results of the model. So unless and otherwise you do this, any modeling effort is not going to be meaningful. So let me go into the next. So typically if you look at the modeling process, you have a real world problem, something like an operating CHTR. And what do you mean by mathematical problem? I need to write using the basic physical and chemical phenomenological laws. I may have to propose mathematical equations representing the temperature as a function of conversion. Now remember, when I try to do this, it may be resulting in one mathematical equation, maybe a number of mathematical equations of different forms. Some of them can be linear, some of them can be non-linear, some of them may be differential equations, some of them may be even partial differential equations. So a set of such mathematical equations, when you solve, you will be in a position to identify for a given temperature what is the exit conversion. So try to solve that, then look at the results. and if you think that the results are reasonable, your modeling effort is going to be over. Otherwise, you go back and probably check up some of the assumptions that you made in order to improve the accuracy of this model. So typically, if you try to look at the modeling process can also be iterative in nature until and unless you are satisfied with the accuracy of the results that are obtained by solving the model. Then coming to the part of simulation, just look at this general definition. Simulation is the act of representing some aspects. Please concentrate on this. Why am I restricting myself to only certain aspects? As I said in the previous example, my purpose is to identify the optimum temperature. So when you are developing the mathematical equations, why do I have to write equations representing the conversion as a function of pressure? Maybe any other such variable which is affecting conversion. This is not the purpose for which you started developing the model. So limit yourself to the so-called objective in developing the model. As you keep on incorporating more and more process variables, probably the model can become complex and it may pose some problems while solving that model equations. Now, what do you mean by simulation? Probably may not be exactly clear from this statement. We will try to discuss further. What do you mean by this manipulation? Now, once again, with respect to the example that we are talking about, we wanted to find out the optimum temperature. So if I was given permission to experiment, what I would have done, operate the reactor at different temperatures, measure the exit conversion. Now, on one side, you have the actual system, right? We wanted to find out the conversion obtained from this actual system as a function of temperature by experimentation. Because this was not permitted, what we are doing, we try to replace this actual system with a model and do what exactly you propose to do here. So now, though you are not permitted to do experiments on the real system, now I will be able to experiment with the model. Solve the mathematical model or the set of mathematical equations subjected to a different temperature each time, calculating the corresponding conversion. So when you do this exercise, this is what is meant by manipulation. You are manipulating the input temperature, solve the mathematical model in order to obtain the corresponding conversion. So doing this repeatedly, you will be able to establish data representing conversion as a function of temperature. Maybe utilizing the data, you will be in a position to either graphically find out the optimum solution or maybe use any other optimization technique to calculate the optimum temperature. So this is what I mean by manipulation. Now let us divide this further. Simulation is a mathematical model. Then we are trying to predict how the process would behave if it was constructed. In fact, we are developing the mathematical model which is going to duplicate the performance of the original system, that is the reactor. Then what exactly you mean by simulation? Do you think there is a difference between simulation and modeling? Okay. Now let us look at the second part. Once you develop such a mathematical model, you may be able to vary the flow rates, compositions, temperatures, pressures or any such variables at the input level, solve the mathematical model to calculate the outputs. For example, with respect to the same example that we are talking about, each time we are solving the mathematical model subjected to a different set of temperature, a different value of temperature. Now the moment you change the temperature, once you are able to solve the mathematical model, you will be able to calculate the conversion, right? In the same way, if you have a process model instead of one reactor model, then you will be able to calculate the outputs like product flow rates, product compositions, energy requirements, so on and so forth for different input conditions. You may be able to study the effect of change in flow rates, change in compositions, change in temperatures, change in pressures across the entire process with an objective of identifying what is the corresponding outputs. So this is what is meant by actually simulation. Earlier we simply said manipulation. Now this manipulation can be done with respect to flow rates, compositions, temperature, pressures or any such process variables with an objective of calculating what is its effect on a particular output or maybe on the entire set of outputs. Now coming to the typical definition of process simulation, you can say flow sheeting is a synonym to steady state process simulation. I am restricting to steady state conditions for the time being. You know, most of our chemical processes are going to be designed to operate under steady state conditions. So under steady state, using a computer to perform some of these calculations is what is meant by process simulation or flow sheeting. You should be in a position to do mass and energy balances, sizing, design or rate equipment, and then also perform costing calculations. Why do I have to resort to a computer to do these calculations? We know how to write mass and energy balances, how to design equipment like heat exchangers, reactors, distillation columns, and probably we'll also be knowing how to calculate the cost estimation of various costs, operating costs, fixed costs, then calculate the profit and so on without the use of a computer. Why do you think the computer is required? Where is the need for computer? Why is it involved in the definition of flow sheeting itself? As I said, if you try to go back, we wanted to calculate the outputs by varying some of these parameters which are affecting the output. So the same set of calculations are going to be repeatedly calculated. For example, in the case of reactor example, we can say the same mathematical equations are repeatedly solved, each time subjecting the same set of equations with a different temperature. So there is no change in equations, the only change is with respect to the input temperature. So repeated calculations, computers are going to be very handy. You will be able to solve the same set of equations quite easily compared to the manual effort. So if you are trying to calculate some of these only for a predetermined set of values, you don't have to use a computer. When you want to repeatedly solve the same set of equations, same set of calculations for different input conditions, that's where computers are going to be handy. Now, with this background, can you put some of these tasks in a particular order? What comes first, what comes later, and what is the end? Based on the discussion, you can identify that in order to simulate, you need to have a mathematical model. Why do you simulate? Probably one of the purposes is to optimize, though this may not be the only possibility. So modeling can be considered as a prerequisite to process simulation. And one of the purposes for simulation could be optimization. So just to summarize, modeling is the construction of a mathematical representation of a system. In fact, for any given system, you can propose a number of models. But unfortunately, in the normal usage, people very frequently use modeling and simulation as synonyms. In fact, this is not true. There is a clear-cut distinction between modeling and simulation. A particular unit or a process can have different models. Simplified models to very large complex models. Each of the models can be used to simulate. Each of them may be able to give you different accuracies, right? So there is a clear-cut distinction. You should never be using modeling and simulation as synonyms, right? You know already, in order to simulate, you need to have a model, right? But because despite this distinction, be careful. Many people might be using them as synonyms, but don't try to make this mistake after this session. Now, simulation itself is derived from the Latin word simulare, which means pretend. So if you further extend the other synonyms for pretend, they can be considered as imitation, pretension, false appearance, feigning, and fake. So some of the typical examples that we normally come across in our daily life: artificial jewelry, right? Or simulated pearl, artificial pearl. It's not original, but it is going to imitate the performance of the original pearl, original jewelry made up of gold, right? So in other words, Probably I can summarize this discussion between modeling and simulation with this statement. Modeling, simulation can be defined as an experiment performed on model. So as I said, whatever you wish to do on the operating reactor, because that is not going to be permitted because of cost and maybe other safety reasons, whatever you wish to do in real experimentation, now you are able to do it by developing a model which is going to duplicate the performance of the original system, and whatever experimentations that you are planning to do on the original system, now you will be able to do on the model. Okay. So just to reach a conclusion, simulation is used in many areas, in many disciplines. You know now that no airline would allow pilots to fly aircraft for which they do not have relevant experience on a simulator. Nowadays, we also have car simulators. Before you are able to go into learning how to drive a car, probably you are given some simulation experience on a car simulator. So experiences with the real life situations can be costly, can be dangerous, right? Time consuming. Probably simulation is a tool to avoid some of these problems. Now, having identified what is meant by modeling and simulation, now let us see why do we have to carry out process simulation. For example, think of yourself as an entrepreneur. You would like to set up a process plant, produce a product, and then maybe make profit. Okay? Then how are we going to answer some of these questions? How much I need to produce? Even before that, what product I need to produce? How much to produce? What are the various equipment I may have to make use? How they have to be connected? And what should be the operating conditions that I must operate, that I must use in order to operate these equipment, and whether I'll be able to make profit or not. So do you think you will be able to answer these questions? So let us elaborate this further. So by conducting rigorous steady state mass and energy balances with accurate estimates for necessary physical properties, the performance of any process can be predicted with a reasonably good accuracy. See, estimating the physical properties, the accuracy of this estimation is ultimately going to reflect the accuracy with which your simulation results are going to be. There is a direct correlation between them. We know how to write these mass and energy balances, whatever may be the system that you have in mind. That's not a big deal. What do you mean by estimating necessary physical properties? Let me take a small example and demonstrate this particular aspect. For example, when you want to perform energy balance, you need to estimate the enthalpies, and then mostly, unless and otherwise you do these enthalpies, you will not be able to do the energy balance. Now, for example, I have a particular stream, let us say benzene and a toluene mixture. To start with, let us say they are equimolar, available at a particular temperature and pressure. Maybe you also know the flow rate. Some certain values are given to you. Now, I would like to estimate the enthalpy of this particular stream involving two components with equimolar composition available at a particular temperature and pressure. How can we do this? So when I typically look at this problem, people normally come across with this example or with this equation. Delta H is equal to integral m Cp dt. Enthalpy, absolute enthalpy cannot be calculated, but we will be able to calculate the enthalpy changes by taking some reference temperature. So this integration is normally done between some reference temperature to the required temperature that you have in mind. Right? Okay. Do you agree with this equation? Arbitrarily, we may be defining the enthalpy of this reference state as 0. So the absolute enthalpy is nothing but the enthalpy change compared between the reference temperature and the present temperature. This probably is all right. But the question that I have here is, what should be the specific heat that I should consider? Should I consider the specific heat in the liquid phase or vapor phase, or maybe a mixture of liquid and vapor? Do you think you will be able to carry out this integration without addressing the issue of what is the phase condition of the given system? So benzene toluene at this given temperature and pressure, without knowing whether it is a liquid, maybe a vapor, or maybe a mixture of liquid and vapor, do you think you will be able to make use of this specific heat? Okay. So how do we resolve this problem? You know how to conduct your VLG calculations. I may not be going into many details, but you please think of this. By plotting PXY diagram, you know how to plot this P versus X1, Y1. Right? So for this given composition, you try to calculate at the given temperature, plot the PXY diagram by assuming the system is existing as a liquid. So once you do this, let us say this is the given composition. Now what do you think is this pressure? And similarly, assuming this composition as vapor, you can also calculate this pressure. So identify these two pressures and compare these two pressures with the available pressure or given pressure. Remember, this calculation is done at the given temperature. So what is the top line? This is going to be P versus X, whereas the bottom one is P versus Y. So what do you call this pressure as? Is it bubble point pressure or dew point pressure? So please think about it. Now, if the given pressure is above this pressure, now what is the condition of the system? It is a subcooled liquid. If the pressure is equal to this pressure, then we call it as saturated liquid. If it is equal to this pressure, it is saturated vapor. And if it is below this, we call it as a superheated vapor. But if it is somewhere in between, then we have a mixture of liquid and vapor, anywhere between these two pressures. Of course, similar calculations can also be inferred by doing TXY diagram at the given pressure. The same information can be obtained. For the time being, let us say after doing this analysis, one more issue is, what type of model are you going to make use to develop this PXY diagram? Do you think you have to make a decision here? So should I assume both the phases as ideal, which in such a case we have Raoult's law, YIP is equal to XI PI saturated. Now remember, if the pressure is quite high, assuming both liquid and vapor phases to be ideal itself can result in a large error. Now still you will be able to consider the vapor phase as ideal, but consider the liquid phase as non-ideal. Then you have one more term coming into picture, gamma I. And if you want to consider both phases as non-ideal, you will have to put phi I. Now how are you going to take which one of these equations should I be considering? Should I be assuming both phases as ideal, only liquid phase as non-ideal, or both phases as non-ideal? So depending on the decision, there can be a change in the accuracy of your result. That is one aspect. The second aspect is, how are you going to calculate this gamma? Again, even in your undergraduate study, you might have come across certain models like Van Laar equation, Morgule's equation, Wilson equation, and so on. In addition to this, now you have many other sophisticated models like Uniquac, Unifac, and for that matter, any equation of state approach can be used to calculate these gamma and phi. So which one of those models are you going to make? So let us say this is one decision which can influence your accuracy. For the time being, let us assume that you have decided that it is either saturated vapor or superheated vapor for the time being. Then how do I get specific heat? For example, if you consider the specific heat, you know, typically we have specific heat in the ideal gas state divided by R is usually represented as A plus BT plus CT square plus DT power minus 2. Right? Remember, you will be able to note down the values of A, B, C, D for any pure component. You should be able to represent the specific heat as a function of temperature. But what do you mean by this? Only when the given component is in ideal gas state. Again, depending on the pressure, assuming ideality itself may lead to lot of error. So you know already, the ideal gas enthalpy is not a function of pressure, but only a function of temperature. So depending on the pressure, if you assume that it is ideal, this also is going to be not very accurate. That is another issue. And for example, if you try to make use of this, remember these data are available for pure components, but we are dealing with a mixture of benzene and toluene. How are we going to evaluate the property of the mixture? Are we going to take some kind of mole fraction average? Again, there are some mixing rules which will also come into picture, especially when the pressures are high, to have an accurate result. Having done this, if you are using something like ideal gas state, how are we going to calculate the actual enthalpy in the real gas state? Probably you might have come across one possibility in your undergraduate study. You know delta HR is equal to delta H minus delta H in the ideal gas state. So we were able to calculate this using this equation. Now we need to know this. So somehow estimate this residual enthalpy. Again, you might have come across one or two alternatives at undergraduate level. So remember, a simple property like enthalpy, how many decisions have to be taken, and see if the decisions are not correct, it is going to lead to lot of error. So that is the problem involved with estimating physical properties accurately. So if you are able to do that, you are sure of getting accurate results, because the mass and energy balances for any equipment or any process, there cannot be two different ways of writing it. The only difference here is what are the physical properties that you are making use in order to estimate those energy requirements. If there is an error in estimating these physical properties, that error will percolate into even your results. So that's going to be very, very important. In fact, in a complex process, about 70 to 80% of your computational time normally is involved in estimating the necessary physical properties. So that is the importance of the role of physical property estimation in process simulation. So if you go into the details, what are the different types of uses for process simulation? You can design a new process. You can evaluate different plant configurations, modernize and revamp existing plants, expansion, in other words it is called as retrofitting, plan for production changes, assessing compliance with environmental regulations, debottlenecking, monitoring, optimizing and improving plant yields and profitability. Please go into this. I may not be having time. You look at what is meant by debottlenecking, retrofitting, revamping, so on and so forth. Probably let me spend a couple of minutes to explain one or two concepts here. Consider, for example, I have an existing plant. Be careful with this discussion. This is an existing plant which is in operation, and this plant is producing a particular product at the rate of, let us say, 100 tons per day. This requires obviously some raw materials, some utilities, heat and work and so on. Now the question here is, can I increase this capacity to 110 tons per day using the same equipment? Is it possible? So do you think we'll be able to answer straight away? So if this is a whole plant, it may be difficult to understand this problem. Consider, for example, one of the units involved in this process happened to be something like a heat exchanger. So this heat exchanger originally was heating in the plant, heating the process fluid from one temperature, let's say T1 to T2. Maybe the flow rate was M1 dot. Thus, based on this data, this heat exchanger was designed, installed and being operated. Now, with respect to this question, what I am trying to do, I am increasing the flow rate by 10%. Now, do you think you will be able to get to the required temperature of T2? So, is there any possibility of using the same equipment with this increased flow rate to reach this required temperature? So, there may be certain possibilities, like you may be able to increase the steam flow rate, or you may be able to increase the steam pressure, or you may be able to increase the steam temperature. Remember, if you want to increase the steam temperature and pressure, maybe you may have to replace the boiler that is supplying the steam. But you may be having enough capacity of the boiler to give you more steam. So depending on the possibilities, you can think of using probably increasing the steam flow rate to supply the excess heat in order to get to this requirement. But be careful, when you try to do this, you should not be in a position to overcome or bypass any safety restrictions or design restrictions with which this heat exchanger is designed. You should not be exceeding the allowable pressure drops. You should not be causing any, you should not be overtaking any safety limitations. So more or less you try to do this kind of an exercise for each and every equipment. Majority of the equipment, by modifying certain operating conditions, you may be able to handle this extra capacity. But whatever you try to do, some equipment may not be able to handle this extra capacity. We call them as bottlenecks. So when you consider debottlenecking, remove that resistance. Try to debottleneck, reduce the resistance that is caused by some of these equipment, right? What do you mean by this? How can you do that? Maybe you try to replace that single equipment with a new equipment, or put another equipment of a smaller size, operate that in series, so that you will be able to handle this extra capacity. Normally, the amount of investment that goes into this kind of replacing one or two equipment in the entire process, vis-a-vis the profit that you will be able to get, the return on investment will be quite attractive. In the same way, you will be able to look at even other things. For example, there is a new technology available which was not so when you design the equipment and operate the process. For example, the separation column can be replaced with maybe a membrane unit. A new membrane has been designed. Now it may be more effective. So see what will happen if you try to replace the distillation column maybe with an alternate technology, whether it is going to improve your profit or not. So that is called as revamping, right? Retrofitting, expansion of existing plants. What are the changes that you would like to do? Revamping, retrofitting, bottlenecking, debottlenecking, they can be somewhat related. So you may be modernizing. Now, sometimes the process simulator can also be effectively used to take care of production changes. This typically happens with refineries. Depending on the market situation, you may have to fine-tune the product rate. So you have the possibility of producing more diesel, more petrol, or more kerosene by fine-tuning the operating conditions. So depending on the market demand, suppose you would like to maximize the production of one of the petroleum cuts. Do you think you will be able to manually change the temperature and pressure and see whether you are able to get to the required product? This is not possible. So simulation probably can be a handy tool. In the same way, there can be lot of variation between different types of petroleum crudes with respect to their properties. So whenever you want to change the crude from one form to one type to another type, like Bombay High crude, compare it with Gulf crude, then do you think you will be able to manually change the operating conditions in order to get the optimum performance? That is atrocious, right? So if you are able to have the properties of a different crude, try to simulate, optimize whatever you require, find out the operating conditions and employ them in your practice. So this can also help you in such a way. Now coming to the case of a process simulator, it's an engineering tool which can do all these calculations automatically. this may probably give you a wrong idea, in the sense you should be capable of defining the problem. So you should have the capacity of using the capabilities of a process simulator, right? Which we will probably identify in some of the other sessions. So it will be able to do mass and energy balances, do the property estimations, design equipment, cost, and probably even optimize. So the advantage of a process simulator is you have accurate description of physical properties of pure components, and you will be able to estimate the properties of complex mixtures by using different property methods. So you also have models for a large variety of reactors and unit operations, and depending on the complexity of the mathematical equations, even numerical methods are available to solve those mathematical equations all at one place. So these are some of the commercial software that are available in the market. Probably the market leader is Aspen. Now HYSYS is also owned by Aspen Tech. Together, probably they are enjoying something like 70% of the market share with respect to process simulation. And I may be failing in my duty unless I talk about this. GIGO, garbage in, garbage out. I'll just give you one example. Consider the system ethanol water. You know, this is going to form an azeotrope. But if you assume this particular mixture as an ideal system, you will be able to design a simple distillation column to practically separate them into pure components, or with 99.9 or whatever purity that you want. This is of course far from reality. The separation can be done only up to the azeotropic composition by using a single column. But if you make the mistake of assuming this as an ideal system, now you will not be able to get to this reality. So the outputs depend on what kind of inputs, what kind of decisions that you have taken. If you have taken some kind of a bad decision, Aspen will not be able to know this, or any process simulator will not be able to know this. It will accordingly dutifully calculate and gives you the output, which may not be really representing the actual practice. So the expertise, the domain knowledge of the user will come into picture in making appropriate decisions. In other words, the output is going to be as good as the input that you provide. If you make a mistake, the mistake will reflect in your output. So please keep it in mind. Now when you look at, we have seen what is simulation, what are the advantages of using process simulation, where are we going to make use of it, right? So as I said, I may not go into the details. This is the place where we may be looking at process simulation. So perform mass and energy balances, design and cost estimation with an objective of optimization. For example, I said how much to produce, what equipment to use, what are the operating conditions. Take such decisions in the beginning, do these analysis, keep on manipulating these decisions with an objective of optimizing them. So in fact, this whole issue is related to three parts: synthesis, process simulation, optimization. So the result of process simulation maybe is to optimize. Now for example, if you are trying to optimize parameters like flow rates, temperatures, pressures, concentration, we may call it as parametric optimization. But if you try to look at changing the equipment of one form to the other, like you replace a CSTR with a PFR, replace a distillation column with a membrane unit, then we may call it as structural optimization. Synthesis is where you are going to take some decisions based on certain heuristics. So you may not be knowing, you will be taking a decision like what type of reactor I have to use. Should I conduct the reaction in liquid phase or vapor phase? So on and so forth. What kind of a recycle system I have to plan? What type of separation systems I have to design? So based on certain thumb rules, you will be making such decisions. But you will not be able to go into production without knowing actually whether the process is economically viable or not. So this is where simulation will come handy. This is the task of process design. Then If you look at the total design project, we have designed the process on a paper. Now you need to bring it to reality. The second part is what is known as project engineering. Of course, this list by far is not exhaustive. Some of the important aspects only I have included here. You want to identify where do you want to set up this plant, within the location, how are you going to set up various equipment, then what about piping and instrumentation diagrams, utility line diagrams, piping design, engineering drawings, fabricate, construction and manufacture. In fact, you can go into many other details as well. So, simulator is going to help you at least in designing a new process, or from the uses you can see even in the case of an existing process, you will be able to improve its performance. So with this, I would like to close down this session. Maybe we will concentrate on certain other aspects in the next